Caching. A cache is a temporary, high-speed storage layer that keeps frequently accessed data closer to your application, so future requests can be served without repeating expensive work. One user becomes 1,000. 1,000 becomes 1,000,000, everyone asking for the same thing. Your database runs the same query again and again until it can't keep up. What if most requests never had to touch the database at all? That's exactly what caching does. Think of a database as a massive warehouse. Every piece of information stored somewhere inside, and finding it takes time. Now imagine a receptionist at the entrance who already has the most requested files ready. That receptionist is your cache, a temporary, high-speed layer that keeps frequently accessed data closer to your application. Computers are built like cities. The closer data is to the processor, the faster it can be reached. CPU cache about a nanosecond. RAM about 100 nanoseconds. Redis half a millisecond. A database 20 milliseconds or more. Caching works by moving frequently used information closer to your application. Caching happens at every layer. Your browser caches images, CSS, and fonts so it never re-downloads them. A CDN stores copies around the world so every user hits the nearest edge. Inside your application, frequently used objects live directly in memory. Once you have multiple servers, a distributed cache like Redis keeps them all in sync, and even the database caches its own disk pages in memory. Cache aside is the most common pattern. The application checks the cache first. If it's a miss, it fetches from the database, stores the result, and returns it. Future requests become almost instant. It's easy and flexible, but the application owns the caching logic. With read-through, the application only ever talks to the cache. The cache loads missing data from the database on its own. Write-through updates the cache and the database at the same time. Consistent, but slower writes. Write-around skips the cache entirely and writes straight to the database, useful for data that's rarely read back. Write-back writes to the cache first and syncs the database later in the background, incredibly fast, but if the cache crashes before that sync happens, the data is gone. Local caches live inside each server. Fast, since there's no network call, but each server can end up with a different answer. A distributed cache gives every server the same shared source of truth, at the cost of a little network latency. And large systems rarely stop at one layer. They stack browser, CDN, gateway, application, and Redis caches together, each one shrinking the work left for the next. A cache is only useful if its data is correct. The moment the database changes, the cache becomes stale, which is why cached invalidation is considered one of the hardest problems in software engineering. Common strategies: expire it after a fixed time, delete it on every write, invalidate it through an event, or simply bump a version number. Every architectural decision is a trade-off. Caching improves performance dramatically, but it adds memory cost, staleness risk, and invalidation complexity. Great architects don't optimize for speed alone. They balance performance, consistency, cost, and complexity. Caching isn't a technology like Redis or Memcached. It's the principle behind every layer of this stack. Avoid doing expensive work twice. So instead of asking which cache to use, ask 4 questions: what should you cache? Where should you cache it? How long should it live? And what trade-offs are you willing to accept? If you enjoyed this video, please like it, comment below, subscribe to the channel, and tap the bell icon so you don't miss the next one.